discussing about the spherical refractive lenses. So one part of the topic that we have already discussed in the last class, that your object was placed in a rare medium and your image was forming in the denser medium, and then also we call that image as a real image. Similarly, today also we'll be discussing about our real image formation, but here we'll be changing the interchanging of the position, like the object will be now placed in a denser medium and the image will be forming now in the rare medium. Like if you see in the diagram here, we have the spherical refractive lenses, the same convex spherical refractive lenses we are using, the object, center of curvature and the pole. Now this is a point object. Suppose a light ray extends from the object and it hits the surface. Okay, and it hits the surface. We know that when the light ray goes from the denser to the rare medium, it always bends away from the normal. Why? Because the speed of light increases. Now, first of all, let us draw the normal here. So the normal will be passing through your center of curvature. This is our normal. Okay. So after this, as we know, this light ray, the incident ray, after hitting the separating the another medium, it will be bending away from the normal. So this light ray will be bending away from the normal and it will be hitting the principal axis. So when it will be intersecting the principal axis, at the point of intersection, here your image formation will be done. So this is your point object and that is your image, and that image is your real image. Clear? Now here let us consider about the angles. This angle is our angle of incidence. Okay, this is our angle of incidence. Let me mark it above. This is the angle of incidence. Then we have the angle of refraction. We have this angular refraction. This is the angle of refraction. Okay, then we have to represent the alpha, beta and gamma angles. So here this angle is your alpha, this angle is your gamma, this angle is your beta. Alpha, gamma, beta. This is similar to the previous diagram only, the alpha, gamma and beta. Same way, you draw one line from this point perpendicular to the principal axis. This is the normal to the principal axis. Mark this as point A. So since we have to derive the formula, we have to use the Snell's law. So for using the Snell's law, what we have to do, you have to calculate the first value of angle of incidence, the angle of refraction. So let us find out the values of this. So first of all, I'll be using the triangle A and O. Okay, A and O. One more thing. From the pole to the object will be your object distance. From pole to the image will be your image distance. And from pole to the center of curvature, this will be your radius of curvature. Now, from the triangle A and O, here I'll be using the tan theta angle, as I've already told in the last class. And since your angles are small, so we'll be not using the tan theta, we'll be directly writing only the angles. So if I use a triangle A and O, here we have the angle alpha. Now if you consider alpha is equals to, okay, let us first of all calculate the value of alpha, beta and gamma. Alpha will be equals to AN by NO, or we can write, because since N is very closer to P, we can write as AN by PO. Similarly, from the triangle ANI, here the angle beta will be equals to AN by NI, or we can write as AN by NI, or we can write AN by PI. Beta we have got, calculate the value of gamma now. So for the value of the gamma, we have to consider ANC. From triangle ANC, gamma is equals to AN by NC. So it will be equals to, we can write AN by BC. Okay, now if I go on putting the values here, AN by PI, since your image is on the right hand side, so this will be plus B. AN by PC, this is on the left hand side. According to sign convention, we have to use minus. So this will be minus R. Here, like if I rub this will be AN by minus of U. Okay, an by minus u, an by v, and an by minus r. Now pause it. You can do write this part first. Now I am moving to the next part. Let us calculate the value of I and r. Now suppose if you want to consider the value of angle of incidence. This is the angle of incidence. Okay, this is the angle of incidence. We have to consider what exterior angle. Okay, exterior angle. We have to consider this as the exterior angle. So we can write gamma will be equals to I plus alpha, or we can write I is equals to gamma minus alpha. So what we have got, the gamma angle, we have got an by minus r. You can see previously, minus alpha, this alpha angle we have got an by minus u. Okay, we can mark this as equation number 1. Similarly, if I want to calculate the value of r, so that r, you can see this angle, this r we can write is equals to gamma plus beta. R will be equals to gamma plus beta. So gamma we have an by minus r, beta we have the beta angle, we have the an by ni plus an divided by v. So an by minus r plus an by v, we can mark this as equation number 2. Okay, next step what we'll be doing, we'll be using the Snell's law. So let us use the Snell's law now. So by using Snell's law, we know that sine of angle of incidence by sine of angle of refraction is equals to the refractive index of medium 1 with respect to medium 2. Now since the light ray is going from medium number 2 to medium number 1. Okay, so here we have to write sine I by sine r is equals to n1 by n2. Next step, I'll be doing cross multiplication. It will be I into n2, it will be equals to r into n1. Now go on putting the values now. I into n2. I'll be skipping one step. What I'll be doing, because both the terms has a and has common, so we can cancel that part. So the left out will be 1 by minus r, this will be plus 1 by u equals to r. So this will be not r, this will be n2. This will be n2, this will be n1. In bracket we have to write minus 1 by r plus 1 by v after putting this from these equations. Now rest, what we have to do, separate the values of r. So it will be minus of n2 by r, so it will be plus n1 by r will be equals to n1 by v. This if I put on that side, so it will be minus of n2 by u. So this is our equation for the spherical refractive lenses. Okay, so this is the second formula. So these two formulas that we have done, the object placed in a denser medium and object placed in a rare medium. These two formulas we have to use in the next topic that we are going to do, that is in the lens maker's formula. So these formulas is important. Okay, these formulas are important for the rest of the chapter. So we'll be continuing the next part, that is the lens maker's formula. Students, let us look out about the lens maker's formula. So the lens maker's formula, for that I am using a convex lens. Okay, this is a convex lens. This is a center of curvature C2. This is a optical center. This is a center of curvature C1, because we know that the lens has two surfaces. Okay, so one surface will be towards this side and the other surface will be towards this side. And we can consider that this convex lens, it is made up of two spherical refracting lenses. Okay, so for that I have split the diagram into two parts. You can see the below diagram. Okay, this lens can be divided into two parts. Now based on this, we can consider, like suppose this is point X, this is point P1, this is Y, and this is point P2. Okay, P1 and P2 are the poles. Now, if I consider that, as I have already told, that the lens is being made up of two parts. There are two spherical refracting lenses. This is one part, this is one part. So we can divide this lens into two parts. Suppose if we consider that there is a point object. This point object, so when the light ray from the point object, it will hit the lens. Okay, it will hit the lens. Then what happens? Because of the refraction, your image will be forming on the right hand side of the lens. Okay, on the right hand side of the lens. So, because of the refraction, your image will be forming somewhere here. This is your refraction. And this image that is formed is your real image. But there is a concept behind here is that the lens that you have taken, since I have told it is made up of two parts, suppose if the second part is not present, that is a XP2Y surface, if it is not present. Okay, this part, the second half of the part, if this part was not present, then what would have happened? The image that was formed there, the image will be not forming there, it will forming at a different point. Okay, so where it will form? Firstly, let me draw the normals first. So from C2 I have to draw one normal. This will be one normal. The other normal will be from optical center, center of curvature C1. Okay, so these are the two normals that I have drawn. Now if you consider that, suppose if your second part of the lens it is not present, then what will happen? This image, okay, this image will not form there. It will be forming at a somewhere point a little bit far away from that point I that I have drawn previously. Okay, but since the second part of the lens is present, because of the change in the medium, okay, because of the change in the medium, what will happen? This point I, okay, this point I, because really it will not happen here, this is a virtual point. Okay, this is a virtual point. The original image that will be forming after the refraction of the lenses, let us look about that. But as we know, there will be a bending inside the lens. Okay, there will be a bending inside the lens. So because of that, this point I, okay, this point I, which is a virtual image here, this will behave as a virtual object for the second part of the lens. This point I will behave as a virtual object for the second part of the lens. That means your object is somewhere located inside the lens. Okay, it is located somewhere inside the lens. So that's why your image, what will happen? Your image will be forming somewhere little here. Okay, this will be your image. The image after the two part of the lens. Clear? Now I will be splitting the diagram. Now you see, I will be splitting the diagram. How does the principle works? So you can complete the diagram first. Okay, you can complete the diagram first. So you can do one thing. This you can mark it as a continuous line, will be a real image. This you can mark it as a dotted line. This will be a virtual object which you can mark as I1. Don't forget to give the direction of the rays. Okay, these are very, very important, and these are based on some marks also. Now, suppose I have divided lens into two parts as it is shown in the below diagram. So this is your object O. This is the center of curvature C2. Okay, this is point P1. This is for Y here. XP1 Y. So the object here. This will be the point object from where the incident ray is falling. Now after that, this center of curvature, that is a point C2. Okay, center of curvature C2, and this side we have the center of curvature C1. So let me draw a normal here. I cannot draw this normal because the second part of the lens is not there. So from here, if I draw a normal, the light ray will bend from here. Okay, the light ray will bend from here, because as we know, when the light ray goes from rare to the denser medium, because this is a glass medium, this is a denser medium. So when the light ray goes from the rare to the denser medium, the light ray bends towards the normal. This is your normal. Okay, So it will be bending towards the normal. Clear? This is, I think this is not clear. This is your dotted line. Okay, so this will be your image formation. And this image formation, it will be nothing but, it will be your image I1. Is it clear? So this is your I1. Let me go to the next part. So the second part of the lens. Now what will happen, this I1, as I have already told, this will behave as a virtual object for the second part of the lens. That means this object is being placed inside the lens. It is inside the lens, okay? This is a virtual point. This point is real, it is really inside the lens. So that's why what we have to consider, suppose this is a ray, we consider this is a center of curvature C1. I'll be drawing a normal from here. This is a normal. So when the point object, if you consider the light ray, okay, the light ray, this is the object inside the lens. So the light ray, what will happen? It will bend away from the normal. It will be bending away from the normal because the light ray is going from the denser to the rarer. This is the normal. So it will be bending away from the normal. But the point, the virtual point was somewhere here. This was our I1 and this is our I. So this is our diagram. Okay, this is our diagram. So this is how the diagram is being splitted. So you can see the how does it works. Now let me go to the how to calculate the lens maker's formula. For that we need both the formulas that we have done previously. Suppose for this one, for xp1y, here your object is in the rare medium. You use the first spherical refracting lenses formula. Okay, spherical refracting lenses formula. So let me denote the values here. Here, this is your object distance. Okay, this is the object distance. This is your radius of curvature R1. And we consider this as a distance V1. There are two diagrams, okay, I'm splitting it. There are two diagrams. Draw it separately, don't combine with it. So there are two diagrams. So for the next one, this we have radius of curvature. So this will be C2. Radius of curvature R2. Okay, radius of curvature R2. Then we have the other points like the point I and the point I1. This is your real image distance and this is your V1. This V1 will be the object distance for the second part of the lens. Now let me use the formula. So if I use the formula, we have the formula minus n1 by u plus n2 by v is equals to, it is given as n2 minus of n1 divided by, it is r1. It was r, because I am using the first lens, so we have to use r1. Okay, I am using r1 and image distance here, it is your, here you can see, the image distance is given as v1. So this will be your v1, object distance is the same. Mark this is equation number 1. Similarly, for xp2y, our formula we have for the xp2y surface, we have minus of n2 by v, or we have the n2 by u plus n1 by v is equals to, we have n1 minus of n2 divided by r, but I am using here r2. And here your this object distance for the second lens, object distance, because this is a virtual object, so object distance will be your v1. You have to write this as v1. Okay, minus n2 by v1 plus n1 by v is equals to n1 minus of n2 by r2. Next step, what I will be doing, I will be taking from here, I will take minus as a common. So minus n2 minus n1 divided by r2. Okay, divided by r2. This side will remain as same. You mark this as equation number 2. Now after this I will add equation 1 and equation 2. Equation 1 plus equation number 2. So if I add equation 1 and 2, so it will be n1 by u plus n2 by v1 minus of n2 by v1 plus n1 by v Okay, then equals to we have from the formula we have n2 minus n1 I can take as common. It will be 1 by r1 minus 1 by r2. You can see from equation 1 and 2. Okay, 1 by r1 minus 1 by r2. So next you can see this and this get cancelled. So it will be minus of n1 by u plus n1 by v is equals to n2 minus of n1 into 1 by r1 minus 1 by r2. Okay, then we have taking n1 as common, I will be putting on that side minus of 1 by u plus 1 by v. I will be putting n1 on that side. Okay, so it will be n2 minus of n1 divided by n1 bracket 1 by r1 minus 1 by r2. Now minus 1 by u plus 1 by v, this I can write as n2 by n1 minus of 1, it will be 1 by r1 minus of 1 by r2. Next, n2 by n1, this I can directly write as n, refractive index, n minus of 1, 1 by r1 minus of 1 by r2. Okay, so we have got the formula. You can check the formula for up till where we have got minus 1 by u plus 1 by v, n minus of 1, 1 by r1 minus 1 by r2. Next, what we can do, if I take object distance as infinity, if suppose your object distance, if u is equals to infinity, as we know in a convex lens, if your object distance is infinity, your image distance forms at focus. Okay, so v will be equals to your focal length. So replacing this formula, 1 by infinity is 0, no need to do that. I will be placing directly the v, 1 by f is equals to n minus of 1, 1 by r1 minus 1 by r2. So this formula, okay, this formula is called as a lens maker's formula. Clear? So we have done the lens maker's formula. This is also an important topic for this chapter. So in the next class we'll be discussing about the lens formula. Thank you.